Hello guys, welcome back to my channel Algorithm Avenue. Since our previous videos, we have been discussing about the different types of gradient descent algorithms. First is batch gradient descent, second is stochastic gradient descent, and third is mini batch gradient descent. Okay, we are differentiating these three different types of gradient descent algorithms based on how many times you update your weights and bias parameters in an epoch. Okay, how many times you update your weights and bias parameters in an epoch. When it comes to batch gradient descent, you consider entire dataset as a single batch, and in an epoch you update your weights and bias parameters single time. Okay, you update your weights and bias parameters single time. Okay, when it comes to stochastic gradient descent, you consider each row of data, okay, each row of data as a batch, and you update your weights and bias parameters for each row. Okay, for each row in an epoch. Let's say we have n rows of data, you update your parameters n times in a single epoch. Okay, this is the entire discussion on stochastic gradient descent. Now let's see mini batch gradient descent. When a dataset is given to you, you divide the dataset into different types of mini batches. Okay, different mini batches, and in an epoch, how many mini batches you have, that many times you update your weights and bias parameters. Let's say you have 10 rows of data and your batches is 2, which means you will be having 5 batches, and you train your 5 batches. Now in a single epoch you update your weights and bias parameters 5 times. Okay, as you have 5 batches, 5 mini batches, you update your weights and bias parameters 5 times. Okay, this is how we differentiate three different types of gradient descent algorithms. Okay, now let's see how we actually update the weights and bias parameters. Okay, when it comes to weights, W new is equal to W old minus learning rate dou L by dou W old. Okay, let me repeat it again. W new is equal to W old minus learning rate dou L by dou W old. Okay, here W new is the new weight that you are updating. W old is a old weight minus learning rate, that is an hyperparameter, and dou L by dou W old, that is W old is your old weight, loss is your loss value. Okay, loss value with corresponding to that row. Okay, corresponding to that row or entire batch of data. Okay, means you are differentiating, you are doing the partial derivative of loss with respect to weight value. Okay, this is how you update weight. Now bias, how we update bias is b new is equal to b old minus learning rate dou L by dou b old. Okay, b new is your new bias, b old is your old bias, learning rate is a hyperparameter, L is the loss value. Okay, L is the loss value, and B old is the old bias value. Okay, here you derivate the loss value, you do the partial derivative. Okay, you do the partial derivative of the loss with respect to old bias value. Okay, this is how we update the weights and bias parameters. Okay, but when you observe these formulas, you see that you will be having this partial derivatives values. Okay, now how we actually determine this partial derivative values with respect to different types of gradient descent algorithms. Okay, now first let's see for the batch gradient descent. Okay, for batch gradient descent, the derivative with respect to bias is dou L by dou b. Okay, dou L by dou b is equal to minus 2 by n. Okay, n determines the total number of rows in your data. Okay, as in batch gradient descent, you consider entire dataset as a single batch. So you're considering entire dataset. Okay, entire dataset, that is from 1 to n. Okay, that is from 1 to n determines the total number of rows from first row to n number of rows to determine the partial derivative. Okay, minus 2 by n summation of I is equal to 1 to n yi, that is the true output, minus yi hat, that is the predicted output. Yi hat is nothing but mxi minus b. Okay, mxi plus b, that minus gets multiplied and gets minus b. Okay, this is the partial derivative with respect to b value, that is bias value. Okay, now let's see for how do we actually update the weights. Okay, how do we actually update the weights? Okay, now you see that you see an extra term over here, that is xi. Okay, why this term actually came here is, now let's say we have three rows of data. Okay, sorry, three features in our data set, that is x1, x2, x3. These are our three features in our data set. Now with respect to x1, we'll be having an parameter, right? Okay, we'll be having an bias term. Okay, with respect to x1, we'll be having a bias weight parameter. With respect to x2, we'll be having one weight parameter, and with respect to x3, we'll be having one weight parameter. Let's say this is m0, let's say this is m0, this is m1, and this is m2. Okay, these are the corresponding weight values with respect to x1, x2, x3. Okay, now as your derivative is with respect to m0, if your derivative is with respect to m0, means you're considering this first column. Okay, you're considering the first column data, that is the x1 feature. Okay, so you'll be writing here xi1. Okay, sorry, x1i. Okay, x1i. Okay, you're considering the entire first column of the data. Okay, now when you're calculating the derivative with respect to m1, okay, with respect to m1, that is the second column of the data, you'll be writing x2i. Okay, you'll be writing x2i. Similar goes with the x3 feature as well. Okay, now when it comes to the formula, dou L by dou beta, okay, dou L by dou m, that is weight, is equal to minus 2 by n. Similarly, here n determines the total number of rows. Summation of I is equal to 1 to n yi, that is the true output, minus yi hat, that is the predicted output, into xi. Okay, into xi. I have already explained why we actually use xi over here. This is how we calculate the derivatives with respect to batch gradient descent. Okay, now let's see for the stochastic gradient descent. In case of stochastic gradient descent, you consider single row of data as a batch. Okay, single row of data as a batch. So what you actually do in a stochastic gradient descent is, you run a loop for I is equal to 1 to, okay, I is equal to 1 to in the range of n. Okay, from 1 you will be running till n, and you will be considering for the first row you'll be updating the weights and bias parameters, and similar again the loop runs, and for the second row you'll be updating the weights and bias parameters, and similarly you update the weights and bias parameters for the n rows. Okay, this is how you do the weights and bias updation. So that is why you don't write summation over here. Okay, here for determining the weights and bias parameters, new weights and bias parameters, you are considering entire data set. Okay, entire data set, but here you are considering a single batch. Okay, sorry, single row of data as a batch. So that is why you don't write summation. Okay, that is why you don't write summation over here. Okay, so our formula will be minus 2 into ya minus ya hat, and the dou L by dou m is equal to minus 2 into ya minus ya hat into xi. This is how we update the this is the formula of derivative with respect to weight, and this is the formula of derivative with respect to bias in stochastic gradient descent. Why actually I have not written mini batch gradient descent is, in mini batch gradient descent you will be having batches where the rows in the batches are random. Okay, now let's say we have a batch, in a single batch the rows are not sequential. Okay, rows are not sequential, they are random. Okay, so you don't know from where to start this summation value. Okay, you don't know from where to start this summation value. Okay, it may start from 10, it may start from 20. For different batches you start the summation value from different for a different row value. Okay, for different row value. So that is why I have not written this value. Okay, you generate some random integers in a batch, and you update the weights and bias parameters. Okay, I'll be explaining the entire formulation. Okay, entire implementation in the desktop screen, and we'll be considering a data set, and we'll be applying these formulas. With us we'll be we'll be applying batch gradient descent on the data set. We'll be applying stochastic gradient descent on the data set, and we will also be applying mini batch gradient descent on the dataset and we'll be comparing the results. Okay, before going into our desktop screen, let me show you one thing. Now while applying, okay, in desktop screen, okay, actually in while you write your code, you can't determine the summation value. Okay, you can't specifically write and code for the summation value. So what you actually do is, you see that this operation is mean operation. Means let's say you have 5 data points and you are dividing with 5. Okay, n is equal to 5 and you have 5 different data points and you are calculating the summation and dividing with the n value. Means you are performing the mean value. So you write, instead of this, okay, instead of this you write np dot mean. Okay, you will be calculating the mean value of this entire data. Okay, you will be calculating the mean value of this entire data. M and X. M and X are matrices, and this term, okay, you determine this entire term, right? This term and this term are two different matrices. Now here you need to perform matrix multiplication. So to perform matrix multiplication we use np dot. Okay, np dot, that is dot product. We perform dot product between this entity and the other entity. Okay, first is this mean value and the second is you do the matrix multiplication, that is the dot product. Okay, now let's perform the code implementation on a dataset and compare the results of stochastic gradient descent, batch gradient descent and mini batch gradient descent.
Yeah, welcome back guys. Now let us see the code implementation of batch gradient descent, mini batch gradient descent and stochastic gradient descent. Okay, first in my first cell I have imported necessary libraries. First import numpy as np. Next from sklearn.datasets import make regression. Okay, why I have imported this library is to generate an custom dataset. Okay, to generate custom dataset I have imported this library. Next import pandas as pd. Next from sklearn.matrix import r2 score. My r2 score is the measurement of the model performance. Okay, my r2 score is the measurement of model performance. Okay, next x comma y. Okay, x contains all the input features, y contains my target variables. Okay, x comma y is equal to make regression. Okay, make regression, n samples is equal to 10,000 samples. That is, I'll have 10,000 rows of data. Okay, n samples means how many rows of data you want. I want 10,000 rows of data. Okay, that is 10,000 rows of data. In features is total number of input columns. Okay, total number of input columns. I have selected 5 so that I can have 5 input columns, that is feature values. Okay, next is n underscore targets is equal to 1. Okay, I want single target, so that is why I have put it as 1. Okay, now this entire piece of code is written to prepare an custom dataset. Okay, to prepare an custom dataset I have written this piece of code. Next data is equal to pd dot data frame. Now what the data I have made, okay, what the data I have prepared, now I am trying to display the data. Okay, I am trying to convert that data into a data frame and I am trying to display the data frame. Okay, pd dot data frame, my first feature value is feature 1, next correspond feature 2, and next is feature 3, next is feature 4, feature 5 and my target variable. Okay, now this is my random data. Okay, this is my random data which contains 10,000 rows and 6 columns, or which 5 columns are my input features and 1 column is my target variable. Okay, this is my entire random data. Okay, now after getting my data, the initial thing I have to do is I need to perform training and testing split. Okay, I need to train and test split my data. Means some amount of data I need to give for training and some amount of data I need to give it for testing. So for that, from sklearn.model selection import train test split. Okay, first xtrain xtest ytrain ytest is equal to train test split. Okay, what I am trying to split x and y variables. Okay, I am trying to split x and y variables. My test size is 0.2. Okay, my test size is 0.2. that means I'll be having 20% of data as test and 80% remaining 80% of data as my training data. Okay, 80% of data is my training data and 20% of data is my testing data. Means among 10,000 rows, my 8,000 rows goes for training, and remaining 2,000 rows goes for testing. Okay, now I am trying to determine the shape of xtrain and xtest and ytrain and ytest. Okay, xtrain dot shape is equal to 8,000 comma 5. Okay, this is my shape of the xtrain, and this is the shape of xtest, that is 2,000 comma 5, and this is the shape of ytrain and ytest, that is 8,000 comma 2,000. Okay, till now I have prepared a custom dataset. After preparing my custom dataset, I have split that into train and test split. Now from here we'll be writing our custom batch gradient descent class. Okay, we'll be making our own batch gradient descent class, and we'll be implementing on our data. Yeah, this is the batch gradient descent class I have built. Okay, now we'll be applying this batch gradient descent class on our dataset. First what I am doing is I am building a class, that is batch underscore gd. Okay, that the name of the class is batch underscore gd. Now in the next piece of code I am writing I am determining my constructor. Okay, I am building my constructor, that is def underscore underscore init, which has 3 arguments, that is self is a default argument, learning rate and epochs. Okay, these two are my arguments. Now self dot coefficient is equal to none, self dot intercept, that is bias, is equal to none, and self dot learning rate is equal to learning rate, self dot epochs is equal to epochs. Now I have built on 2 functions, that is fit function and predict function. In fit function, what I will be doing is I'll fit my training data. After fitting my training data, from training data what I will be doing is I'll calculate the loss. I'll calculate the loss, and I'll be updating my weights and bias parameters. Okay, in my entire fit method, my aim is to determine optimum weights and bias values. Okay, optimum weights and bias values. Okay, now I'm fitting my training data, that is xtrain and ytrain, to the fit function. Okay, self dot intercept. Okay, self dot intercept is equal to 0, that is initially I'm initializing my bias to 0. Okay, self dot coefficient is equal to np dot ones, means I'm initializing my weight values to 1. Okay, xtrain dot shape is of 1 means, okay, what is xtrain dot shape of 1? Okay, this is xtrain dot shape of 0, this is xtrain dot shape of 1, that is 5. Okay, actually how many number of features we have? 5 features, right? Okay, 5 features we have, means we need to have 5 ones, that is weight that is corresponding to feature 1 is equal to 1, weight that is corresponding to feature 2 is equal to 1, and so on up to weight corresponding to feature 5 is equal to 1. Okay, I'll be getting 5 ones over here. Okay, now for I in range self dot epochs. Okay, for I in range self dot epochs, I am directly fitting my entire training data and calculating the weights and bias parameters. Okay, I'm calculating the weights and bias parameters for my entire training data. Okay, I'm considering my entire training data as an batch. I'm calculating the weights and bias parameters. Okay, before calculating the weights and bias parameters, first to determine the loss, what I need to calculate is y hat value, that is a predicted output value. Y underscore hat is equal to np dot xtrain self dot coefficient. Okay, what is the formula that we have to calculate the y hat value? Y predicted is equal to mx plus b. Okay, where m is the weight values, okay, weight matrix, x is the xtrain matrix, plus b is the bias. Okay, same I am implementing over here. Now I need to, after calculating the y hat, I need to update my weights and bias parameters, right? What is the formula to update the bias parameter? B new is equal to b old minus learning rate dou L by dou b old. Okay, here we have b old, we have learning rate. What we have to determine is dou L by dou b. Okay, sorry, dou L by dou b old. Okay, so I am considering the dou L by dou b old as my intercept derivative. Okay, intercept derivative is equal to the formula I am applying over here. Okay, the bias updation formula I am applying over here, that is minus 2 into np dot mean of y train minus y hat. Okay, this is the derivative value. I'm putting same over here. Okay, the intercept derivative value I'm multiplying with learning rate, which gives me self dot intercept value, that is the updated bias value. Similarly with respect to quotient, okay, I'm applying the same formula over here. Okay, what I have written on the whiteboard, the same formula I'm applying over here. Okay, minus 2 np dot y train minus y hat, we are multiplying with the extra term, that is x train, and we are dividing with the total number of samples. Okay, extent dot shape determines, extent dot shape of 0 determines the total number of training samples. Okay, we are calculating the quotient derivative, and this is the formula to update the quotient derivative. Okay, sorry, quotient value, that is the weight value. Yeah, after getting my optimum values of weights and bias, I'm writing the predict function to apply it on the test data. Okay, I'm applying the optimum weights and bias values on the test data. How do we actually calculate the predicted output of the test data? We'll be writing y is equal to mx plus c. Okay, where m is now optimum. Okay, optimum weight value, and bias is the optimum bias value. Okay, that you are determining over here. Okay, in the predict function. Okay, next gd is equal to batch underscore gd. Okay, I am giving the learning rate as 0.01 and number of epochs as 100. Okay, I am giving the learning rate as 0.01 and number of epochs as 100. Okay, next I'm fitting training data into my fit function, and I'm fitting the test data into my fit function. Okay, sorry, in my predict function, and calculating the ypred value. Okay, in fit function I'm fitting the training data, and in predict function I'm fitting the test data and calculating the ypred value. Okay, now I'm determining the R2 score between y test and ypred. Okay, y test is my true output and ypred is my predicted output. Among them I am calculating the R2 score, which is coming out to be 58.3. okay, for batch gradient descent for 100 epochs I am getting the R2 score as 52.3. okay, next, now after batch gradient descent, now let's try to build stochastic gradient descent. Okay, now class stochastic gradient descent. Okay, I have determined the name of the class. Now next I am writing a constructor which has same by default same arguments, that is learning rate and epochs. Now I am writing the fit function. Okay, in the fit function the only difference you will be having is you will be writing another loop which iterates through the each row. Okay, for loop you iterate through each epoch. In the second for loops you iterate through each row. Okay, this I in range of epochs is the for loop which iterates through the epochs. This j in range of extend dot shape of 0, extend dot shape of 0 is 8000. Okay, extend dot shape of 0 is 8000, means you iterate through 8000 rows. Okay, you iterate through 8000 rows. Okay, now in that 8000 rows I'm generating random integers. Okay, I'm generating random integers. Okay, in stochastic gradient descent what you do is you generally select random row values, right? Random rows you select. So similarly I'm doing over here, idx is equal to np dot random dot randint, which generates random rows between 0 to 8000. Okay, between 0 to 8000. Now I am calculating the y hat value for the index. Okay, for the index, that is for that corresponding row. Okay, for that corresponding row I am calculating the y hat value. After calculating the y hat value, similar calculation is done. Okay, to update the weights and bias parameters. Okay, in the previous batch gradient descent I have done the mean. Okay, I have actually done the mean in the intercept derivative, but here I am not doing the mean. Okay, why? Because we'll be working with corresponding with respect to the single row. Okay, we are working with corresponding single row, that is why we are not writing the mean value. Okay, we are not taking the mean value. Okay, intercept derivative minus 2 into corresponding, okay, with respect to that idx value corresponding training data minus y hat predicted output, and this is a formula to calculate the intercept value and same coefficient derivative and corresponding coefficient value. Okay, here we are updating quotient and bias values. Okay, that is weights and bias values. Now we are taking the predict function and we are fitting the test data. Okay, after fitting the test data, I'm taking 0.01 as my learning rate and 50 as my epochs. I'm fitting my training data and I'm fitting my test data and calculating the y-pred value. Okay, now I'm determining the R2 score between y-test and y-pred. Okay, it is coming out to be 48.6. Okay, 48.08. Okay, 48.08 is my R2 score with respect to 50 epochs for stochastic gradient descent. Now let's implement mini batch gradient descent. Okay, I have created the class mini batch gradient descent. Okay, in the constructor I'll be having one extra argument, that is batch size. Okay, batch size is my extra argument. Okay, in mini batch gradient descent. Okay, now here this is my batches and learning rate and epochs are my same arguments as previous. Now I am calling the fit method. Okay, now I'm writing the fit function which takes the extract data, okay, sorry, training data, and gives the optimum values of weights and bias values. Okay, now for I in range which iterates through the epochs, and this second for loop, okay, this second for loop iterates through the batches. Okay, let's say we are having, okay, now let's try to calculate the total number of batches over here. Okay, extend dot shape of 0. What is extend dot shape of 0? It will be 8000. Okay, it will be 8000, right? 8000 divided by batch size. Okay, now let's say my batch size is around let's say 10. Okay, no, okay, let's say 100. Okay, my batch size is 100, means in each batch I'll be getting 100 rows of data. Okay, now 100 8000 8000 divided by 100, which comes out to be 80, means this J loop iterates through 80 batches. Okay, 80 batches. Okay, this is the for loop which iterates through batches. Okay, this is the for loop that iterates through epochs. Okay, same, I'm calculating the, I'm generating the random value. Okay, that is a, let's say idx is equal to random dot sample. Okay, what it actually does is now let's say we have a batch with 5 rows of data. Okay, now that 5 rows of data that is divided into mini batch, that 5 rows of data must be random. Okay, that 5 rows of data in a mini batch must be random. So to generate this 5 different rows in a batch, to generate this 5 different rows, okay, 5 different random rows in a batch, I am writing this piece of code. Okay, now what it actually does is, let's say we have a batch. Okay, let's say we have a batch. Now the indices of the rows in that batches will be 80, 200, 500, 60, 50. Okay, in this way they will be random. Okay, to generate randomly we use this piece of code. Okay, which runs from 8000. Okay, which runs from 8000 comma, okay, means 8000 samples. Okay, from 0 to 8000, how many we need, how many actually we need, that is equal to batch size. Okay, now let's say batch size is equal to 5, means we need from 0 to 8000 5 different id indexes values, 5 different indices values which correspond to 5 different rows. Okay, 5 different random rows. Okay, this is the idx value. Now I am calculating the similarly y hat value with respect to 5 different indices. Okay, indices, sorry, with respect to 5 different indices. Now I am calculating the updated bias values. Okay, I am updating the bias value by calculating the intercept value, and here I am calculating the intercept derivative value, and similarly I am calculating the coefficient derivative value, and I am calculating the coefficient. Okay, in this piece of code I am fitting my training data and calculating the updated weights and bias parameters. Okay, I am updating the weights and bias parameters and calculating the optimum weights and bias values. Okay, here I am fitting the test data. Okay, here I am fitting the test data. Now MBGD is equal to mini batch gradient descent. Batch size is equal to, now my batch size is equal to 8000 divided by 200. Okay, 8000 divided by 200, which corresponds to be around yeah, it corresponds to be 40. Okay, my batch size is 40. Okay, I have 200 batches and my batch size is around 40. Okay, learning rate is equal to 0.01, epochs is equal to 100. I'm fitting my training data, I'm fitting my test data and calculating the y-pred, and I am determining the R2 score for 100 epochs, which is coming out to be 49.5. Sorry, 49.8. For batch gradient descent, I have got an R2 score of 52.3 for 100 epochs, and for mini batch gradient descent, I have got 48.086 for just 50 epochs. For in case of batch gradient descent, I use 100 epochs. In case of stochastic gradient descent, I have just got it for 50 epochs. Now when it comes to mini batch gradient descent, I'm using 100 epochs. But getting around 49.8 accuracy. Okay, R2 score. Okay. Yeah, actually I have used an random data, so I'm getting this kind of R2 scores. Okay, but what actually happens is when it comes to batch gradient descent, you'll be getting for 100 epochs. Let's consider for 100 epochs, you'll be getting some R2 score, but for same 100 epochs, you'll be getting some better R2 score, for stochastic gradient descent. And for the same 100 epochs, you'll be getting much more better R2 score when it comes to mini batch gradient descent. Okay, this is the difference between three different gradient descent. Okay, I have considered and custom data set. So you can find this difference in the values. Okay, this is the entire video on code implementation of batch gradient descent, mini batch gradient descent, and stochastic gradient descent. Okay, meet you in the next video. In the next video, we'll be discussing about the back propagation algorithm. Okay, I like you to not miss the next video. So hope you like this video. If you like the video, please like, share, and subscribe. Thank you.